The next talk is by Kim Larsen, who is a professor at the Department of Science at Aalborg University within the Distributed Embedded Systems and Intelligent Units, and the director of ICT Competence Center CISS, and who has several other posts and is one of the most active researchers in modeling and verification. And in particular, he's one of the coordinators of the tool Opal, which is the most successful tool for working with timed automata, as well in academia as well as in industry. And this talk, which we will be giving, is also based on this tool, and it's based on a very important recent application now. So right, let's start then. Thank you.
Thank you very much, Ernst. Hope you can hear me.
Yes.
Okay, very good. Yeah, thank you for the invitation to this workshop. When I was given this task of talking about predictive maintenance, at some point I realized that what we have been doing for the last 1.5 years, since April 2020, in some sense, must have been dealing with the biggest worldwide predictive maintenance problem, namely, to take all kinds of predictive action so that our health system and society as such do not break down. So way back there in 1.5 years ago, we were given a grant very quickly by the Grundfos Foundation. Actually, it's called Paul Du Jensen Foundation. And the task that we were given was to use this tool, UPL, to the best of our ability to do something with this COVID-19. So actually, there were many of us that in our group, Peter Kjell Jensen, Kenneth Dyrk, Jørgensen, Marius Mikrosionis, Marco Muniz, Danny Paulsen, they were just throwing whatever they had in their hands, and then we spent a lot of effort in trying to attack COVID-19 with UPL. So why do I think this is a predictive maintenance problem? This, what you have in the center, I took from the workshop announcement, but we are dealing with maintenance, right? COVID-19. We really are interested in doing something so that healthiness in society, in terms of number of deaths, infected, seriously ill people, how many people are getting hospitalized or coming into intensive care or even dying, that we are on top of that. In terms of what does optimal mean, of course, we want to impact society as little as possible. We are going to close down things, we know that, but it will cost something, whatever we do in terms of jobs, in terms of finances that are being lost, or a reduction in social life, all these things that we have hated for these now almost 2 years, right? So it can be very difficult to put it up into some metric where we just have a solid number, but these are definitely things that we care about. What could be critical system components? I think the health system, how many are hospitalized? Is it going to break down that particular system? Something you can think of. This is definitely something that has been very important in Denmark to look at. And what are the actions we can take? Well, we can lock down things like schools, entire regions. In Denmark, we have what's called parishes, which are smaller regions, workplaces. We can insist on testing, or we can do we can have contract testing apps that can help us get knowledge about the situation. We can do vaccination that we are doing right now, right? So there's a big range of actions we can perform. So what I will do in this talk here is to give you our take on how to model, because we have a model-based approach, such an epidemic, and it can also be applied to many other epidemics. We have what we call SEER and SEER, or SEER, depending on whether you have incubation time, hospitalization, and recovery phases as well. And I'll show you how we can model these in different ways in UPL, ranging from ordinary differential equations to full agent-based models. And then I will, in the second part, apply these to northern Jutland, and right now we are applying it to Denmark to get an understanding of what is the effect of different actions, lockdowns, or what should be opened or what should be closed, and what about testing and tracing. And actually, just 1 month ago, we based on this effort, we are now a member of the expert modeling group of Statens Serum Institute, the Serum Institute of the Danish state. So I think this is really, they think that we have something to offer. I think this is amazing. I didn't know anything about epidemics before this. So when we talk about epidemic models, there are these reaction networks where you see a system, an epidemic, in terms of how many people are healthy. It's called susceptible. How many people are infected? How many people are removed? That is, they have one way or another passed through the infected phase, and now you don't have to consider them anymore, right? So here they might recovered or they might be dead. I mean, but they're not into the equation anymore. And then you have different rates that sort of governs the transport of a number of people from one phase in this reaction network to another one. So you have this removal rate here, and in particular you have this infection rate. And here it's important that this beta here, that it really insists that a healthy person meets an infected person, and then the actual rate by which you have people moving from the S phase to the I phase is beta, but multiplied with the proportion of infected people. This N here is the total population size. Yeah, let me skip that. You can see that maybe the reduction number R, which is often referred to, is actually the fraction of this beta with gamma. So here's the idea: is that it's a closed system. It's perfectly steered. Everybody has the same, you can say, chance of meeting anyone else. Yeah. And most importantly, also when you reach this removed phase, you cannot get infected again. Of course, we know that this is not quite true these days, but this is the assumption here. Here's a slightly extended model where we have an incubation phase called E here. Here you are exposed, but you're not infectious. You cannot spread the disease anymore. For that you need to make a transition to this infectious phase. But and then we have also added here as hospitalization phase and removed phase. So it might be that when you're infectious, you recover without having to go to hospital, or it might be that you need to go to hospital. And of course, if you want to look at this critical phase, critical component of hospitals, you need such a phase. I mean, you could say that once you're in the infectious phase here, everything is up to biology. Your behavior and how you move around in society will not really be so important anymore. So we have really been looking mainly on controlling, having measures that avoid you getting exposed. Actually, already when you are exposed, it's up to biology. These remaining phases here. So that's what I see here. So it's really this beta here where you can do a lot in terms of having social distance, wearing face masks, having kind of restrictions of locking down workplaces, etc., etc. So that's where you can have your maintenance action having an effect on this entire sort of system here. So now how can we model that? Well, you can model things as ODEs. So these modes here, the susceptible, the exposed, and so on and so forth, are really just continuous variables that evolve over time according to differential equations that are sort of the natural representation of the rates here that you see in the network here. So the rate by which the number of susceptible behaves over time, the rate of that is simply proportional to beta times S times I times N, right? And so on and so forth. So if you want to represent that in Newport, well, you first declare all the relevant constant that you think are the good ones. So here, actually, the beta, where do we have it? The beta component here is actually gamma times this BRN, and gamma is this 0.3 over. So this is something that the colleagues we have in control theory were very helpful in estimating actually these parameters here. Here we have a setting with 1,000 people, and in the beginning there is like 1/10 of the population that is infected. And then we can just write down these differential equations. They look like this here. There's only one mode that this hybrid system, dynamical system as it is, can evolve in, and we just write in the invariant of that one mode these differential equations, and then we can do simulation, and you can actually see how the population in terms of distributed over these compartments, as it's called, S, E, I, H, and R, evolves. If I look at the H, it's so small, so we can really see here that over time, it's out of these 1,000, it seems that it's only less than 2 people that are actually hospitalized. So that's one very deterministic model. Another way of modeling it is to use continuous time Markov chains. So what goes into this continuous time Markov chain? Well, the state of that is actually the count in terms of integers, how many individuals are susceptible, how many individuals are exposed as integer numbers. So the states of this continuous time Markov chain is actually a 5-tuple of integers. And then we model these transitions here as actually reactions that will have different rates of firing, and of course, and will have an effect on this configuration in terms of incrementing or decrementing the number of individuals that will be in these different compartments. So here is the reaction of going from S to E. It will decrement S and increment E, and this is the rate by which this transition will fire. There's a precondition in that, of course, you need both to have susceptible and infectious people in order for this to fire. But then again, we can use our statistical model checking engine, in this case here, to actually also again here to get an idea as to how these different compartments will evolve over time. So you can see here the number of susceptible goes down, and the number of recovered goes up, as you see here. But now when you look at the hospitalized situation, it's no longer deterministic. You actually get some idea as to there can be quite a variance in how many people will be hospitalized in this stochastic model. So that's one model you could favor. You can also do some more fancy statistics in terms of what is the expected the probability density over these different counts in the hospitalizations. So if I were to make a statement, I could say there are 3.48 people in average being hospitalized with this confidence interval, 95% confidence interval. So this is a relatively fast way of doing analysis. When you will see later, we will go to these agent-based models. Actually, each individual, so now we had 1,000 individuals, but each of these 1,000 individuals will actually be a continuous time Markov chain, as you see here. So it will be 1,000 copies of that. And here we keep track of each individual. What mode, what healthiness state are you in? Are you healthy? Are you exposed? Are you infectious? And then these transitions here of this individual will be governed by these rates, as you see here. So in particular, the transition of going from healthiness for the healthy state to the exposed state will have this rate here, which still depend on the total number of among the 1,000 being infected and the proportion of that with respect to the total population size. And there's a little bit of keeping count on incrementing or decrementing the contribution to this infectious state seen from each one of these individual components or persons, individuals. So we can do again, simulation so this is a good UPAL SMC model, and we could do simulation, and you see almost the same plot and almost the same statistics. In fact, it varies only very little. And we really, as you will see a little bit later, we really would like to use this agent-based platform here, agent-based type of model here. The only problem is that in order to do a simulation up to a given time point, let's just say 2 months or whatever, here it was just 80, yeah, maybe this were 80 days or 80 time units in this abstract model here, but this will now grow quadratic in the number of components. So this is not really good. So what we have been doing, and let me be a bit vague here, but we have simply and the reason for this quadratic move is that when we do statistical simulation of this model here, there will be races between components as to who will make the transition from one state to the other one. And the average time step of this of the time between such transitions will actually be 1 over n being the number of components here. So yeah, so the time step will be smaller and smaller. The expected time step will be smaller and smaller given the number of components. So what we will do is actually we move to a continuous time event distribution to a discrete time event distribution. So we actually only can allow transitions to take place at regular time points, but now it will not just possibly be one person that changes its state, but there can be several person that changes its state. So when you see what happened here, so we will have a time-driven model instead, where still we have the 1,000 or 10,000 persons out here, but now there will be a certain probability that after whatever amount of time you take as your time take, let's say it's 4 hours or 1 hour. In our analysis, it's 4 hours. So every 4 hours there will be a certain probability. After that tick, there will be a certain probability that that you, to begin with, you pick that probability threshold, and then according to that, you will either with that probability still stay healthy, or you'll move to the next state here. Yeah. So so what you see is you pick P according to some so to some distribution that is governed by these by this beta and this fraction here, and R is just you pick uniformly over between 0 and 1, and then you simply compare here. So in effect, this is you can say the probability by which you go to the next state. And if you do this, maybe this was not the most clear description of that, but you get almost the same result when you do statistical model checking here. But what's really nice is that you only in order to simulate up to a given time horizon, you only need the complexity will grow with linear in the number of components, and that's going to be all extremely vital for our analysis, that it scales, the scalability of it. So here in this one slide here, I'm just comparing the performance of these different types of analysis that I just presented. So let's now try to see how we put all this into action in different ways. So way back last year in the autumn, we had a lot of trouble in Denmark, in particular in northern Jutland. This is where I come from. So you see Aalborg here. You see the tip of Denmark, and what you see here are all the municipalities that you have up north here. In fact, maybe you heard about it, but we have a lot of mink farms in Denmark, and also in particular in northern Jutland. And corona was actually spreading among minks, and there was also seemingly the tendency or the possibility that corona could move from minks to human beings. So in parallel with what I'm talking about here, there was actually a decision by our Prime Minister, Mette Frederiksen, that on November 4th, that all minks in Denmark must be destroyed. And this has happened now. All mink farms has been, this was a huge operation. So I haven't analyzed that, but what I have analyzed, or what we did analyze, was actually a lockdown procedure that took place in northern Jutland. Actually, it took place over less than 1 month, almost just 2 days, but it had different phases. In the first phase, you closed all borders of the 7 municipalities, so each municipality was its own little bubble. On 7th of November, you closed restaurants and bars as well. On 9th of November, 40% of school children were insisted to stay at home. So it was even stricter and stricter lockdowns. Then on 13th of November, the restrictions on the school were lifted again. So it was only in effect in 4 days. And the 16th of November, the 7 municipalities the borders were between these municipalities were lifted, but it was one common lockdown zone. And on 20th of November, it was reopened. So then you could think about, did that have any effect? Was it helpful or not? And that was the challenge here, that we actually just at the very end of November, we because there was a lot of political discussion on that, was that really necessary? What was the effect of that? So we tried to answer that question by making models of that. So here is actually, so for each, let me say before I show these models, and I will sort of point to what are the ingredients in the model. There will actually be two, it would be an agent-based model. We have 500,000 people living in this northern Jutland. So there will be 500,000, you can say, components in this UPL model, one per citizen. And of course, we want to keep track of the healthiness status of each individual. But orthogonal to this healthiness status, and I think this is really what makes our agent-based model interesting, what is it that actually, because this is not a well-stirred community. I mean, you only spread the disease if 2 individuals are close to each other. So how can you be close to each other? Well, you could be at the same location. You could be meeting your family at home, or you could be meeting some people at school, or you could be meeting some people at your work. And this is where it's on these locations, or maybe at bars as well, when you were or doing sports. So we have these leisure locations. So we have actually 2 atometers for each individual, namely the healthiness status, but also the venue, the location at which this person is at. And it's only when you have 2 persons being at the same venue, they can actually affect each other. So here you see actually then the healthiness template for each individual. So you can more or less see here you have these. Let me move this up here. You have more or less these susceptible, the exposed, the infectious, and then the recovered phase here. What you see here is that this probability. So it's a time-triggered model. So each 4 hours. There will be computed a certain probability for each individual to moving to the next phase. And where does that probability come from? Well, it comes from calling this CFD of this with these parameters here. And what you can see here is that there is this, there is actually the number of infected, the number of susceptible, and the number of whatever, that is that particular venue. So this agent will itself be at a venue, and this probability will be computed from the number of people of the different categories that are at that particular venue. And then you will, according to that probability, you will progress from susceptible to exposed state. And so, yeah, so, and when you make this progression, you also choose incubation times and infectious time. So the incubation time it's actually not just the rate of an exponential distribution. So we looked at scientific papers from medicine, and you can see that they're actually much more detailed. They're actually, you can say, not exponentially distributed incubation times, but actually it looks more like this. And this time, and incubation time is the time from when you're exposed until you actually show symptoms, if you show symptoms. In fact, only 20% of the people show symptoms. And if you are then show symptoms, then actually the point of time when you then can spread the disease is run by this distribution here. And what you can see here is actually, you can actually, according to this distribution, spread the disease before you actually show symptoms. So it's a much more realistic model, at least we hope. And then this distribution says something about for how long time you will be infectious. So that's the healthiness real model that we're using for our analysis. We also have say that if you are now infectious, then you should stay at home if you are symptomatic, if you're symptomatic, that is, you will show symptoms and you have passed the incubation time, then this is a place where you can you should stay at home, because you should realize either yourself or by testing that maybe you have the disease. So you'll not just move around. And this is what you see here, and then this other automata that we have for each person. So each person has its own venue, and you will each 4 hours you will actually go to the next phase here. So you stay at home, and then once you're at home here, maybe you want to go to work, but you should only do that if there is not a lockdown or work. If you are supposed to,
Sorry, could you come close to the end in the next minutes?
I will come close to the end here.
Yeah. Right. Thank you.
So let me just say here that we are really trying to weave in. So you can model as a third global automata these lockdown phases here, and of course also observe that you stay at home and it's weekend. So we really try to be very faithful to what is what we believe is the behavior of people. And of course, this venue, this particular home, is individual for each person. So let me just say that what we have taken these two templates. We have looked at registers, public registers for home addresses, work addresses, statistics about number of citizens in the different municipalities, pendling, distribution of family sizes, age distributions. And then we have, instantiated a very big UPL model with 1 million components. We have thrown UPL at it, and we got a lot of statistics. So we have laid down, to do one simulation of this big model, it takes a little less than half an hour. So we are very happy for this time-driven technology we investigated. But of course, we have done a lot of analysis. So let me just flash the results. If you take the entire region and you see the evolution over this period in terms of how many people were exposed, then the lower curve says this is what happened during the lockdown, and this is what would have happened if no lockdown had happened. And here you look at one of the municipalities. This is Hjerring, so you can see an even bigger positive effect of of the lockdown that was happening. And here you see Frederikshavn, another one. And here's Aalborg. This is the biggest of the municipalities, and there nothing really happened. This was because this is a big municipality. But what you can say is that approximately in this entire region, 10,000 people fewer were infected due to the lockdown, and in terms of daily infected people, it was 167 persons. So I think this caught a lot of attention. I can say you can. I was in the news very early on 15th of December, made it to some science magazine in Denmark. And let me skip all this other part here and just say that it has this amazing effect that the Serum Institute of the state in Denmark is actually using these agent-based models. For something you didn't see, we had a investigation. We were advising them on what were the good measure in the spring in terms of opening. Should it be schools or so? We made some analysis here, like we talked about, and together with many other analysis, but that was considered in the opening process that we are now well through. Let me stop here.